Okay, so at this point we have several theorems about functions, continuity, the derivatives. We have the intermediate value theorem, the mean value theorem, Rolle's theorem, the extreme value theorem. Now we want to kind of take our understanding of all of those theorems, as well as our understanding of, say, what a derivative is, the slope of a tangent line, and see if we can put it together and actually just graph a given function. And we're going to start with a few functions that you could actually already graph using knowledge and tricks you learned in 171 so that we can see how the tricks work. And then from there, we'll kind of develop a general theorem idea that we can use to actually graph any function. And we'll know it works because we'll work with it on some of the functions that we already know the graphs of. So to start, maybe we'll start with the easiest one I can think of. F of x equals x squared. We know what the graph looks like. It's just a nice parabola. We have a vertex, all that stuff. But if ultimately I want to graph any function, then what would I really need to graph something like that? I'd probably need the zeros. That would be beneficial. I don't need to find them, but knowing where they are is beneficial. Here, the only zero is at 0. And then I kind of need to know the behavior around the zeros and how that affects the shape of the graph. Meaning, say if over here I drew a second function that we already know the graph of, x cubed. Which again, we all know is that elongated s. I kind of missed 0 there, but we'll pretend. And I mean, if all I told you to start was graph either of these functions, and I told you it went through 0, 0, could you figure out what the graph looked like? I suppose in theory you could plot a whole lot of points, but we don't necessarily want to do that, especially when our functions get really complex, because we'll end up plotting tons and tons of points. But, well, if nothing else, I can tell by this graph the parabola goes down and then goes up. This thing goes up and then keeps going up. I think we mentioned in one of the other videos, this ultimately is what's called a saddle point. We'll deal with that later on. There's other names for it too. But is there a way to use our understanding of calculus now to be able to say, well, this goes down and goes up, this goes up and then goes up. But we understand in kind of calculus speak, and even in math speak, this going down means it's decreasing, and then it's increasing. This is increasing, and then it keeps on increasing. And well, we also said, I think earlier in the chapter, that places where the derivative is 0 would be critical numbers. And clearly that will have a horizontal tangent. We've mentioned that before. So that will be a critical point. And we also mentioned, as it turned out, this is a critical point right here for x cubed. We went through all of this when we were defining critical points. And now I begin to see that I kind of have an idea of what I could do. Well, here, on one side of the critical point, the function is decreasing. On the other side, it's increasing. Here, on both sides of the critical point, it's increasing. Which, if I gave you that much information, might be enough to give you an idea of how to graph something. Meaning, suppose over here, I have another function. I told you it goes through this point right here. I'll just make it up. We'll say it's the point 1, 2. And if I told you that was a critical number, well, that would mean you have a horizontal tangent or something. And if I told you the function was decreasing on one side, on the left of it, and increasing on the right, could you get an idea of the graph? Well, yeah, I could at least guess. If I told you it was decreasing on the left, then I'll make it going down on the left. And if I told you it was increasing on the right, I'd make it go up on the right. And at least as far as guesses go, that would be a good guess. Which again, kind of leads to this idea then. Well, if I want to graph something, maybe I should find the critical numbers because, well, I guess using more of the kind of math speak that we have, it looks like these critical numbers are also maxes and mins. I mean, that's clearly a min. The one I drew before was also a min. If I flipped it around, it would be a max. It's not always true, because on the cubic I had over here, that wasn't a max or a min. We actually used that one before to show that. But it looks like these critical points are maxes and mins. And then the only question is there a way using calculus to figure out where the function is decreasing and increasing? Well, yeah, because if we think about, from a calculus perspective, tangent lines, if I drew tangent lines here on the left, all the tangent lines would be going down. They'd be negative slopes. On the right, all the tangent lines would be going up. They'd have positive slopes. So if I have negative slopes, my function is decreasing. If I have positive slopes, my function is increasing. And we've kind of mentioned this in bits and pieces throughout this chapter and throughout all of the calculus we've done. Now we're just kind of putting it together. Because now this tells me if I can find a critical point, we already know how to do that. Set derivative to 0 and find when the derivative is undefined. And then if I look at points around those critical points, if the derivative is negative, it means the function's decreasing. If the derivative is positive, it means the function's increasing. And let's face it, if I told you there's a point where the derivative is 0, horizontal tangent, on one side it's decreasing, on the other side it's increasing, well then you can be pretty convinced that that is going to be a min, because that's the only way you can decrease and increase. And that's actually going to lead to an incredibly important test that we're going to go over. But before we actually write out the test, we can actually maybe practice this. So suppose we have this. F of x equals x squared minus x minus 6. Graph that. Well, let's see. I could try to find the zeros. I could actually factor that. I'm not even going to bother with that here, because I know we could already do that. Are there any critical numbers? Are there any places where I have a horizontal tangent? We know just by looking at it, that's a quadratic, so it's a parabola, which means there definitely is a vertex somewhere. And understanding how parabolas work, that's going to be a max or a min. So find it. Well, take the derivative. That's where the critical numbers come from. The derivative is 2x minus 1. And then to find the critical numbers, we said next, take the derivative and set it equal to 0 and solve. Add the 1, divide the 2, you get x equals a half. Now that's my critical number. If I actually want to find the point associated with it, well, there's a trick here. Just keep in mind, this is 1/2. Don't plug it into the derivative here. You'll get 0. If I want to graph this, I plug the x that I found into my original function, because that's where the points on the graph come from. If I plug in 1/2, 1/2 squared is 1/4, minus 1/2 is negative 1/4, minus 6 is negative 6 1/4, which is negative 25/4. Which means now I have a critical point that I can use on my graph. 1/2, negative 25/4. And I can plot that. 1/2, negative 25/4, we'll say it's like right there. And now again, I know it's a parabola, and yes, there are tricks from 171 that will let me graph this, but we're using this as a guide to see how the calculus is going to work for harder functions that I can't graph like 171. So, I can use my understanding of the derivative, and if you remember 171, we went over a trick, or in whatever 171 class you had, you went over a trick for some of your graphs called a sign chart. And we can actually use the same idea here because I only care about where the derivative is positive or negative because that tells me if the graph is increasing or decreasing. So I do a sign chart and I line up my critical points because those are the places where the derivative is 0. Here I only have 1. Now I do exactly what I did when I did with sign charts in 171. Pick a point on either side of this critical point and plug it into the derivative because we're working with the derivative and see what I get. Well, if I pick a point here, I'll go with 0. I get -1, which is negative. On this side, if I pick, say, 1, I get 2 minus 1, which is positive. And now I know on the left, my derivative is negative, which means my function has to decrease. On the right, my derivative is positive, which means my function has to increase. And now I can get a sketch of the graph. Over here, I have to decrease. Over here, I have to increase. And I get the parabola that I wanted. And again, I stress, I could have done this in 171. I can actually find those zeros by factoring. It's not a big deal. But ultimately, we'll deal with functions that we can't. And it appears by just finding the derivative, setting it equal to 0, and finding where it's undefined, I can find points that are maxes and mins. And then by using a sign chart on the derivative, I can get a sketch of the graph. So really quickly, because we only have a couple of minutes left, suppose I have f of x equals x cubed minus 1. Well, we know I'm going to take the derivative, that's 3x squared, set it to 0, which will give me x equals 0. That's a critical number. It's not undefined anywhere, so there's nothing else to worry about. Now I take this and plug it into the original function, and I get f of 0 equals -1. So my critical point is 0, -1. I can plot that. Now I do a little sign chart. That's the value x equal to 0. Pick a point on either side and plug it into the derivative. If I pick -1, I get -1 squared is 1 times 3, positive, which means the function is increasing. On this side, if I plug in 1, I get 3 times 1 squared, so it's 3. I get positive, so it's increasing. Now I know my graph is increasing on both sides, which means it has to come up. The tangent has to be 0 here, horizontal, and then it goes up again. And I get the cubic that I want. And the idea to keep in mind here, we're only working with basic graphs, but we're going to start working in the next video with more complex ones. And, well, now I can pretty much get an idea of when I'll have a max, when I'll have a min, when I'll have one of these saddle point things that we called it before, by just looking at this. If the graph goes up and up, that's not going to be a max or a min. What if the graph went up and then down? Well, then that would be a maximum point. What if the graph went down then up? We did that on the last one. We got a minimum point. And we can see these tricks that we can use to actually sketch the graph of a function. And like I said in the next video, we're going to work with more and more complex functions and formalize this into the actual formal test.